So students, we are doing combination of capacitors and we have joined the two capacitors in series. And I told you that they will be the charge in series, the charges on the two plates are the same on each capacitor. So you can see that in series charge is same on each capacitor. What about the potential? So you have connected them with potential V. So this potential will obviously be divided in series. So this plate will have potential V1, this plate will have potential V2. Now potential rise is equal to potential drop across these plates. So V1 is equals to V1 plus V2, and we know that C is equals to Q by V. So, and V can be written as Q by C. So what will be the value of V1? V1 is equals to Q by C1 plus V2 is equals to Q by C2, and V is equals to Q by C. Now this will comes out to be 1 by C is equals to 1 by C1 plus 1 by C2. So that's the formula we have for series, that the net capacitance of the capacitors will be 1 by C is equals to 1 by C1 plus 1 by C2. So if we add n capacitors, then it will be keep on adding 1 by C3 and up to 1 by Cn. Now the capacitors are connected in parallel. So we have these two capacitors. Friends, once again I am telling you what's the meaning of means combining in series and combining in parallel. So if one terminal is connected, if one of their terminals is connected, then it is considered as series, because this other terminal there is battery in between. So both the terminals are not not connected directly. But here both the terminals of the capacitors are connected directly. So whether it is the case of capacitors or resistors or even cell, whatever it is, series means that only one of their terminals is connected, and parallel means both the terminals are connected directly. Okay, so here let us see the difference. So here you can see the charge was Q, but here the charge is plus Q1 on this plate and minus Q1 on this plate. So on this plate charge will be plus Q2, and on this plate charge will be minus. So that's the case, and it is connected with potential V. So let V be the potential that they are connected with. Now what will be the total charge here, which is Q is equals to CV, same as in this case. C is equals to Q by V, same in this case. Now here the charge is divided. So here charge was same, but the potential was divided. But here the charge is divided. Q is equals to Q1 plus Q2, and Q is equals to CV, and Q1 will be equals to, so this is C1 capacitor, this is C2 capacitor, So C1, so of course in parallel same potential will be there. So C1V plus C2V. So students, now the net capacitance will be C1 plus C2. So and if there are n capacitors, then keep on adding their capacitances up to Cn. So these are the two simple formulas. So just opposed to the resistances. So in series, if there is resistance, then it will be R1 plus R2. And if the resistances are in parallel, so in case of resistance, we know that 1 by R is equals to 1 by R1 plus 1 by R2. Okay, so opposite to these formulas in case of resistance. Fine. Now let us do one example based on this concept. Example 2.9. So we have a network of 4 10 microfarad capacitors. So this is the first one, this is the second one, and then the third one, and then the fourth one over here. So all of them are have the same capacitance, 10 microfarad, and they are connected to power supply of 500 volt. Okay, so this is shown in the figure. Now what you need to find? A part, you need to calculate the equivalence resistance of the circuit. B part, you need to find the charge on each capacitor. Okay, so this is what we need to do. So charge on capacitor means the charge on the plate with a higher potential, that is Q. Okay. Now you can clearly see that, let us first name these capacitors. This is C1, C2, C3 and C4. And the charges on them, it is given in the question. So charges on them, the charge is plus Q and minus Q on this plate, and then minus Q and plus Q on this plate, and then plus Q and minus Q on this plate, and this plate it's minus Q dash, and on this plate it's plus Q dash. Now you can clearly see that one terminal of C2 and only one terminal of C3 is connected, and one terminal of C2 and one terminal of C1 and one terminal of C2 is connected. So it means C1, C2 and C3, they are in series. So what will be the equivalent circuit of this? So let the equivalent resistance of these three is C dash. So C1, C2, C3 are in series. Now their equivalent capacitance will be given by 1 by C1 plus 1 by C2 plus 1 by C3. So all three are same. So 3 multiply 1 upon 10 microfarad, right? And the C dash will be the reciprocal of this. So C dash is equals to 10 by 3 microfarad. So Now this network has let us draw this network again. So this is C dash and this is C4. Okay, and it is connected with the power supply of 500 volt. So all these three I have replaced with C dash, which is 10 by 3 microfarad. Okay, now these two are connected in. Now C dash and C are connected in parallel. You can clearly see that both their terminals are connected. So this terminal and the other one also. So they are connected in parallel. Now the equivalent resistance, so this is C4, C dash and C4. So the equivalent resistance will be C and it will be given by, so this is the equivalent resistance of the circuit now. So C is equals to C dash, so formula of parallel, C dash plus C4, and that is equals to 10 by 3 plus 10. So that's equals to 13.3 microfarad. So first question we have done. So this was C equivalent of the circuit. Now the B part. What is the charge on each capacitor? So clearly the charge on, they are connected, so we have just studied that charge is same on each capacitor when they are connected in series. So students, see, we have only two things, charge and voltage. Okay, so in one case charge is divided, in another case voltage is divided. So always remember, voltage is same in the parallel and charge is divided. So here in series, charge is same, voltage is divided. So only two things. So these three are series, so they have charges same Q, and C4 already I have written the charges Q dash. Okay. Now the potential difference, so we also have marked them A, B, this is D. So this is A, B, C and D. Now the potential difference across AB is V1, and that will be equals to Q by C1, and this here it will be V2, it is Q by C2, and here V3, that will be Q by C3. So the net drop, so 500 volt in parallel, so 500 volt across this capacitor and 500 across this capacitor. So this 500 will be divided among C1, C2, C3. Okay, so V is equals to V1 plus V2 plus V3. This V is 500 volt, and that's equals to Q by C1 plus Q by C2 plus Q by C3. Okay, and what about here? The charge is Q dash over here, so V is equals to Q dash by C4. So here this voltage was divided, and here so in parallel it is the same. So this 500 volt was divided among C1, C2, C3, and means along C4 the potential difference, or you can say voltage, 500 volt. So this can be written as 500 is equals to Q dash upon C4. So this is Q is same, C1, C2, C3 is also same. So 500 volt is equals to 3Q upon, and the capacitance is 10 microfarad. So this gives me the value of Q, which is 5000 upon 3, and that is equals to 1.7 into 10 to the power minus 3 coulombs. So that's the charge along C1, C2 and C3. And now what about C4? So here this Q dash is equals to 500 into 10. That's what C4 is. Students, one thing we need to do is that this microfarad, when I'm putting this value, you cannot put this value like this. You have to write it in SI units only. So this you need to write as 10 into 10 to the power minus 6 farad, and then this will come out. So here also this you need to put in farad, the SI unit. So 10 raised to the power minus 6 farad, and this will comes out to be, so 10 into 10 to the power minus 6, right? 10 microfarad. So this will comes out to be 5 into 10 to the power minus 3 coulombs. So that's the charge on each of the capacitor. Now let us do a couple of questions based on this, on whatever we have studied in parallel plate capacitor. Yesterday we studied the capacitance of a parallel plate capacitor. So C is equals to Q by V, that's the definition, but C depends on, is directly proportional to the area of the plates and inversely proportional to the distance between them. So this formula we derived yesterday. Now let us do a question based on them. So we have a parallel plate capacitor with air between the plates. So we have this parallel plate capacitor and there is air in between the plates, and the capacitance of this capacitor is 8 picofarad. So that will be equal to 8 into 10 to the power minus 12 farad. What will the capacitance if the distance between the plates is reduced by half? So this is D. Now what I have done is that distance is reduced by half. So the distance is reduced by half. Second thing, this is the first thing I have done. Second thing I have done is I have filled the space with a dielectric whose dielectric constant is 6. So these are the two things that I have done. That I have reduced the space here, it is D by 2, and this I have filled with the material that is dielectric material with the dielectric constant 6. So what will the capacitance of this capacitor? So C dash is the capacitance of this capacitor that I need to find. So if there is air in between, then this formula you can write C naught is equals to epsilon naught A by D, and if this there is dielectric, then you will be writing epsilon A by D. C dash equals to epsilon A by D, and epsilon is equals to epsilon naught K. Okay, so that's the value of epsilon A by D, right? Now so this capacitance is given to us that C is equals to that is the C naught. For vacuum we use C naught, and for medium we don't use C naught here, so that is equals to 8 picofarad. That's given to us. Okay, now when it is filled, then this will the formula, and this also changed to D by 2, so we have this D by 2, right? So C dash is equals to epsilon naught, and value of K is 6 A into D by 2, so 2 will come upside. And what is the value of epsilon naught A by D? Epsilon naught A by D is your this capacitance, so that's 8 into 10 to the power minus 12, so that's equals to 6 into 2 into 8 into 10 to the power minus 12, and that's farad. So this comes out to be, it was 16 is the 96, and 10 to the power minus 12 is pico, so 96 picofarad will be the new. So this was exercise question, back exercise question 2.5 of the NCRT. Now we have another question based on this concept, that is 2.6. So 3 capacitance of capacitance 9 microfarad, they are connected in series, and what is the total capacitance of the combination? So very simple this question. So 1 by C is equals to 1 by C1 plus 1 by C2 plus 1 by C3, and all 3 of them are same, so that's 3 into 1 is to the power 9, so this gives me C is equals to 3. So 1 by 3, so C will be 3, so 3 picofarad. Is it micro or pico? So it's pico. Okay, so this was part A, and part B is that what the potential difference across each capacitor when the combination is connected to 120 volt supply. So it is connected to 120 volt. So obviously the capacitance are same, so it will be equally divided. So obviously the answer is 120 by 3, 120 by 3, 120 means 40 volt, 40 volt, 40 volt. So just obvious. But how will you write it mathematically? So the total that V1, V2, V3 be the voltage drop. So total voltage rise is 120, and the drop is V1 plus V2 plus V3, and so all 3 of them will be same. So you can write here it is 120 volt is equals to, so all of them are same, V1 is equals to V2 is equals to V3, so let it write 3V1. So V1 would be equal to 120 volt. So this is volt, this is units, don't get confused. So this is 120 volt. So V1 is equals to 120 by 3, that is equals to 40 volt. So we have the voltage symbol is V, and its units is volts for the voltage, so don't get confused, the units and the physical quantity. Okay, so students, now let us do the next topic, very important topic from examination point of view, energy stored in a capacitor. So what energy? It's the electric energy that is going to be stored. So this is there on page 80 of NCRT. So we have seen that capacitance is a system of two conductors. So it is consists of two conductors with a charge plus Q and minus Q, equal and opposite charges. And now we want to determine the energy stored in this configuration. So initially we have two uncharged capacitors. So consider initially two uncharged conductors. So capacitor is made up of two conductors, right? The charge is plus Q and minus Q on the plates, on the two. So parallel plate capacitor means both the conductors are plates. Okay, so consider initially two uncharged. So these two conductors have no charge on them. So two uncharged conductors, 1 and 2. Now we are going to transfer the charge from 2 to A. So transfer the charge bit by bit. Bit by bit means delta Q. Very small charge, bit by bit, from 2 to 1. So let us draw here. So these are so this was the first scene, figure A, no charge, and then this figure B. So I'm transferring this charge now to this plate. So I'm transferring this charge. So this plus Q I'm transferring bit by bit. So plus delta Q I'm transferring. Well, let it be Q dash, because here the charges we will be taking Q, so that we don't get confused. So when this plus charge will be taken on that side, of course it will be less positive, so negative charge will appear here, and it will be more positive, so positive charge will appear. Now take one more, so it will be less negative and positive. One more. So, and we are transferring this positive charge from here to here. So there will be a stage when this plate will have the charge Q dash and this plate will have the charge minus Q dash, and you are transferring this. So at a particular stage you are transferring this plus delta Q dash when the charge on the plates are Q and Q dash. So at that point of time you are transferring this charge delta Q dash. So charge from here will be reduced by delta Q dash, and charge on this plate will obviously be increased by Q dash. Okay. So at the end, what will be there at the end? So this is C part, this is the end, this intermediate stage, this is intermediate, and this is beginning, start, no charge at all. And in the end, we will have this charge Q and minus Q on this plate. Okay. So as you know that the work done that we'll do will store in the form of, see, you are doing the work here against the field. So against the field, this work done will be stored as potential energy. That is what about the conservative forces are. So work done against the conservative force is stored in the form of potential energy. So we are doing the work, this positive will repel this positive, and we are doing the work against the electric force. So that work done by the external agency will be stored as potential energy. Okay. So definitely this positive is higher potential and this plate is lower potential. Now we want to calculate the work done, whole work done. So we'll take the work done for this intermediate stage. What is the work done in taking the charge plus delta Q dash from this plate to this plate? How much is the work done? Okay, in taking the charge plus delta Q from this plate to this plate. So very small work done is done. And then we'll integrate this work done and we'll get the total work done. So that's the case. That's what we are going to do. Okay. So we have an intermediate situation where the conductors 1 and 2 are, so write here intermediate stage so that you need to write it theoretically. And now imagine a small plus delta Q dash charge that you are transferring from 2 to 1. So this is intermediate stage. Point number 2. This was beginning, starting stage. This is the intermediate stage where you are transferring the charge. So bit by bit is not required, just this much of the charge you are transferring at particular stage. We were transferring bit by bit, but there came a stage when the charge here is Q dash and here the charge is minus Q dash, and now I'm transferring this charge plus delta Q. So how much is the work done? Small work done in transferring this charge. So delta W is the work done, and that is given by, so work done is equal to VQ. You know this formula. This is actually the voltage, the potential difference, delta VQ you can write. So, and you also write it as VQ also, the voltage, but if you are writing it here it means voltage, the potential difference. So delta Q is equals to, so the potential difference at this point of time is V dash between the plates. So, and I'm taking this charge delta Q from this plate to this plate when the potential difference between the plates is V dash. And now this delta W can be written as Q dash upon C, because I will be integrating this work. So if V dash depends on Q, so write the V dash in form of Q. So V is equals to Q by C, and that's delta Q dash. Now the total work done will be integrating both sides. So this side I am integrating, I get total work done. What about this side? So the work done when Q was 0, and the work done till the charge which is Q. So 0 to Q. And this is Q dash upon C, and this delta I can write it as dQ. Now in 12th class you are very much comfortable with integration. So 1 by C, and so what is the integration of x dx? So that's equals to x square by 2. So 1 by C is constant outside, and so this is Q dash square by 2, and the limits are 0 to Q. Okay. Now the work done will be equals to, put the value of Q dash equals to Q square. So final value minus initial value, put Q dash equals to 0. So 0 by 2 is 0. So that's equals to, so we have C here, not 2. This is C. So we have 1 by 2 q square by c. So that's the total work done, students. So such a simple derivation which is there in the exams. Okay, now we can, if we put the value of q, so c equals to q by v, so q equals to cv. So put this value of q here, what do we get? I get 1 c square v square. So 1 c will cancel out, you will left with only 1 c. So that's another way of writing this formula. And now I have put the value of q, now I will put the value of c. So put the value of c is equals to q by v. So q by v, 1 q will cancel out, so only 1 q will be there, and this v will be in the numerator. So 1 by 2 qv. So these are the formulas. If you have q and c, then find the work done using this, and c and v, then work done can be calculated, and q and v, this formula. So that's the work done. So as you know that electrostatic force is conservative, so it doesn't matter which charge you are taking, earlier, later, no. And another important thing about the conservative force is that as the electrostatic force is conservative, so this work done is stored in the form of potential energy of the system. Okay, now this is the potential energy, this stored in the form of potential energy of the system. So that is now we need to find the energy density. We want to compare two. So when we want to compare the energy stored by capacitor, by two capacitors, so how we are going to compare them? So to compare the energy stored in capacitors, compare the energy stored in capacitors, you have two capacitors, three capacitors, so then you need energy density. So you need to compare them, you need energy density. So what the energy density is? So the energy density is energy stored divided by the volume. So this is energy stored divided by the volume of space. Between the plates of the capacitor. Fine. So we already know that the energy stored is this. So that is U by V. So what is U? 1 by 2 Q square by C divided by volume. What's the volume? Volume is A into D. Fine. Now we'll write the charge in terms of surface charge density. So we know the surface charge density is equals to Q by A. So Q is equals to sigma A. So sigma is equals to Q by A. So, and capacitance also we know the formula of capacitance, that is epsilon naught A by D, right? So So putting the value of Q and C equals to epsilon naught A by D. These are the two formulas that I'm going to put here. So I will get 1 by 2 nu square A square upon C is epsilon naught A by D divided by A by D means that's divided by A by D. Now what will cancel out? This A square is definitely going to cancel out. This D is also cancelled out. And we get the energy density that's equals to one by 2 sigma by epsilon naught. Now I want to find it, write it in terms of electric field between the plates of the capacitor. So I know the formula, we have derived it that here the electric field is 0, here also the electric field is 0, but in between the plates the electric field was equals to nu by epsilon naught. So both the field were rigid. So E upon 2 epsilon naught and E upon 2 epsilon naught, and then electric field was equals to upon epsilon naught, right? So what will the epsilon naught equals to? Epsilon naught equals to what the sigma will be. So sigma will be equals to epsilon naught into E. So put this value over here and I get 1 by 2 so E square upon epsilon naught. So 1 epsilon naught will be cancelled out, and that's what the energy density is. And always all the density we write with small numbers. Not numbers, small letters. So U is equals to 1 by 2 epsilon naught E square. So students, very simple derivation. So energy density is equals to energy stored upon volume. So energy stored we know, that is half Q square by C divided by AD. Simply put the value of Q and C and we get this, and then you can put, so that's also energy density. So it depends on, that's also correct. If you want to write it in terms of surface means charge density, and if you would like to write it in the form of electric field, so that's all about it. Now let us do a example based on this concept. That is example, last example 2.10. So we have a 900 picofarad capacitor and it is charged by 100 volt battery. Very good question from examination point of view. So we have this battery over here, 100 volt. This is going to charge this capacitor, and this is 900 picofarad, means 900 into 10 to the power minus 12 farad is the capacitance of this capacitor. So you need to find how much is the electrostatic energy stored by the capacitor. So energy stored, U, that's the first thing, and the B part is now the capacitor is disconnected, so that's second part. Let us do the first part first. So what do you have? You have C and you have V. So what the formula do you have which is connecting C and V? So we have derived these three formulas over here. So C and V, so that's half CV square. So the potential energy is equals to half CV square. That's what you can store. So that's half into C is 900 into 10 to the power minus 12 and V is 100. So CV square, so 100 into 100. So what will I get? So this is 450. So minus 12 plus 4, and then in scientific notation it will be 4.5 into 10 to the power minus 6 joules. So students, that's the energy that can be stored in this capacitor. Now B part, what have I done is, as the capacitor is charged, so I disconnected it from the battery and I have connected it with another capacitor. And that capacitor, the capacitance is 900 picofarad, same capacitance. So what is the electrostatic energy stored in the system? So now we have to find again of the system. So obviously this the energy is a scalar quantity, so you want to find it for the system, so simply add the energy stored by this capacitor plus the energy stored by this capacitor. Okay, now these two capacitors have so this was plus Q charge and this was minus Q after charging it. So now this charge will be equally divided. Okay, so here the charge will be plus Q by 2, minus Q by 2, and plus Q by 2 and minus Q by 2. So obviously if you join these plates, so this will be equally divided, this charge, and as they are connected in parallel, so they will have same potential. So capacitance is same for both of them, and potential difference, let it be V dash, which is same for both of them as they are connected in parallel. And what will be the charge on each plate? So charge is Q dash, that is equals to CV. So charge here is CV dash. So that charge is Q by 2. Q dash is Q by 2. And what is, so the voltage is also equally divided. So here it was 100 volt when it was charged. So it is also equally divided. So it will be 50-50. So this V dash is V by 2. Like Q dash is also Q by 2. So students, this is important. You can get MCQ also. So what happens is, when you, so V is divided, charge is also divided. So this is what V dash is, this is what Q dash is. Now what is the total energy of the system? I told you that the energy of this system and energy of this system will be added, and you have two things, V and Q. So what is V by this? What is V dash? So it's 50 volt, 100 by 2. And what is Q dash? So that you don't have. So what to do? But you know V and Q. You know Q. So Q you can calculate. So you can calculate Q as CV. So you know the value of C, you know the value of V. So you can calculate that this Q was 900 picofarad. So 900 times about 12 farad into voltage 100 volt. So the charge on the plates of these capacitors was 9 into 10 raised to power minus 8 coulombs. So this charge will be halved, so that will be 4.5 into 10 raised to power minus 8 coulombs. So the energy stored by this is you have all the three formulas. You can use any one of them. You know the value of Q and V. You also know the value of C and V. So energy stored was half CV square. So half CV square plus half C V dash here. This is the V dash. Capacitance is the same. So it's your choice, students. You want to find with this formula or with this. So that's your choice. So you can find it with this, or you can also find this with the half Q dash V dash plus half Q dash V dash. So simply you can put the values. So this formula is, see, the smart thing is that this U is this. So that is equals to half QV, right? Half CV square is this. So this half QV. So we have V and Q. We know the value of Q dash and V dash in terms of Q and V, we write, and then we can use this formula. So this will be a little bit lengthier, but this will be very simple. So half, what is Q dash? Q by 2. What is V dash? V by 2. So plus half Q by 2, V by 2. Okay? And that's equals to, so 2 multiply this, so half means this is actually 1 by 4 QV, right? And this is half QV is this, because okay, you have calculated the potential energy using this formula, but this is also the formula, so it's the same, right? So that's half, I can write it half into half QV. So half QV is 4.5 into 10⁻⁻6 joules. So that's 2.25 into 10⁻⁻6 joules. So the energy of the system is decreased. Here also, from here I know, so this is U dash I can write if I'm using U symbol here. So this is U by 2. So half of U. This is U. So it's half of U. So it is reduced by half of U. So that's important thing, that energy is reduced to the system from U to U by 2. So where has this energy gone? So this energy has gone because this, you can see this charge is flowing, and flow of charge is the current, and when this current is flowing, the heat is lost. And when a charge moves, heat is lost in the form of electromagnetic radiation. You know, the accelerating charge particles, they emit electromagnetic radiation. So in the form of electromagnetic radiation, half of the energy is lost. So don't connect means you think that I have stored the energy in this capacitor. Now let me store the energy half in both the capacitors. No, the energy remained here is 1 by 4 of the total and 1 by 4 of the total. So of the system it will remain only half. So students, so this is all just for the understanding, but for finding this solution, so you need not to use this formula or this one even. Okay, directly use this. So calculated U, you know CV, calculated the potential energy, and thus we know that potential is also equals to half QV, and here we know that V becomes half and Q becomes half. So obviously using this value directly, so that's the answer. So thank you so much for watching today's lecture.